Willie, what'd you say? JVC's unplugged.
My sound on. Okay.
Testing.
That they are staying on task with what they're supposed to do, and ordering really weird stuff on Amazon. They have worked hard all year. As most of you know, thank you, Danny. As most of you know, this has been one project all year. So we do have two groups. They will be presenting. This group will be presenting first, then we'll switch tables out so they have all their prototypes and whatnot in front of you. Let me go help Allison. We're still having technical difficulties. It's one of those engineering IT moments where everything that could go wrong this evening has. So let me see. Nope. I'll press a button. Just give me a second. I'm going to give this to Ariana.
Hello everyone, thank you so much for coming. I did not expect to see so many faces. And this is the climate bottle. And so I am Ariana Konzelman. I am a junior at Carmel Catholic High School.
My name is Sindar Rajendram and I'm a sophomore.
And my name's Sam Schneider. I'm a senior. Our design statement was that we originally wanted to be able to create a water bottle that can both heat and cool water to our desired temperature. But our prototype we have right now, it only cools because we figured that would be the hardest problem to solve.
Our problem statement is that water bottles tend to have poor temperature regulation. So our goal was to make sure that it doesn't become lukewarm by the end of the day, which seems to be a big problem among people who were surveyed. And a lot of previous solutions only aim to fix the problem temporarily. Speaking of the survey, this is our survey, and we surveyed a random 136 high school students and teachers around our school. And although most people didn't drink coffee, most said there was a small margin that said that yes, their coffee does become lukewarm by the end of the day, which is more for when we were going with our heating system. And for our cooling system, we surveyed another bunch of people where most of them said yes, their water bottle gets lukewarm by the end of the day.
Pause for 1 second. Evidently there's no audio.
No audio. It's on.
It's not on.
It is on. It says on.
Does this one work?
Okay, try it.
Testing.
Test.
Oh, it just turned on.
I just clicked it on and off.
You would have to off mic this whole time.
Testing. Any system connection?
Okay.
Connected?
My professor can hear you. Mr. Schneider, or whoever Schneider is here, which just says Schneider. Okay, so we can keep going.
One of them. All right, can we continue?
Yes.
All right. So our previous idea, we hope to create a self-heating and self-cooling water bottle, as was mentioned before by Sam. And although we couldn't go with the heating system, we decided that with the time left over, it would be more beneficial to have a cooling system versus a heating system, because heating systems are very common.
So now we'll move on to the prior solutions.
Yeah, there you go.
The first prior solution we looked at was this 3-in-1 phone charger we bought off of Amazon. On one side of the device, it can charge your phone. Well, on the other side, it will be able to heat and cool your like aluminum can soda. We found that this is quite efficient at heating, but it's not the best at cooling water. We ended up taking this apart to see how it can heat and cool. And we found that it uses what's called a Peltier system using these Peltier plates. These are the results from our testing. You can see that it's a lot better at heating than it is at cooling. The next one we looked at is this Standstill water dispenser. This is very good at what it does. It can both heat and cool water very effectively, but the issue with this is that it stands still. It's not portable, and that's what we want to be able to do. The next one, and by far the most popular, is the insulated water bottle. This is the most popular because it is the most consumer-friendly and simple design out there. It's able to maintain water temperature very effectively, but we want to be able to control water temperature and be able to heat it and cool it. And the last one we looked at, this is the best at heating by far. It's the self-heating teapot. This, it uses a heating coil, I believe, to heat the water, and in our testing, it was able to boil water in about a minute.
So, during our brainstorming process, we contemplated different ways of how we could heat or cool our water bottle. So for heating, we contemplated taking heating elements such as heating coils and using it to heat up our water. And for cooling, we contemplated using a fan and heat sinks and Peltier plates to cool it. And these are pictures of how we plan to assemble our water bottle. Since we're working with extremely flammable and a lot of flammable materials and a lot of wires, we took safety very important. I had the key role of getting to hold the fire extinguisher. So
I will be talking about prototyping and all the different processes it took to prototype. First, before we could prototype, we had to understand what systems we were putting together. So what is a Peltier system? A Peltier system is made out of very basic parts such as a heat sink, a Peltier plate, and a fan. And those all together work together to cool down a metal plate on the top. So what's inside of a Peltier plate? This took a lot of research, but a Peltier plate is made out of 2 ceramic plates on top and bottom, and inside there are pellets, and these are made out of bismuth alloys and tellurium alloys, which work with an electric current that runs through, and if the polarity is changed, it can make it hot or cold, so one side on the top will be cold while the bottom will be hot. So we also had to set controls, and on the next slide you can see a line of how the controls actually worked. It's pretty steady for the most part, but it does go down, which is important to keep in mind with testing if it's any better than the controls. Our first prototype was the hot glue gun prototype, which is a very rugged design where we took apart a hot glue gun because it also has ceramic inside of it, and we attached it to a aluminum can and put water inside. We tested it, and we saw that the results weren't the best it's as best as a hot glue gun would be, but on the next slide we can see our results where it does work somewhat, but not to the extent that we want a heating system to work, especially after taking 20 minutes to only get maybe about 10 degrees warmer. Then we continued on and we went to our soldering iron test. Our soldering iron test was more efficient, and there were some issues because we tried different areas of the can of where we put the soldering iron, and we got very different results depending on the location. On this slide, you can see where we had 2 different locations, and it shows how the results are different with the testing. And without liquid on the inside it's different than if it's on the outside and so on. Our next prototype was the Teapot Prototype, and on the next slide you can see how efficient it was. After 1 minute it went pretty much to boiling. Another prototype, now we go into the cooling prototypes. The cooling prototypes were a little bit dangerous because we had a very fast motor, and this is our fan prototype. Although it worked, it didn't work very well, and it just was too unsafe to have in a water bottle, and we didn't feel like refining it because it would have to just be blowing on metal, which wasn't suited to our needs.
So after a lot of research on cooling systems, we learned that a lot of cooling systems had something called a heatsink in it. So on the next slide, we tried making our own because we didn't think it would be that hard to put a bunch of pieces of metal together. However, it didn't work, so we ended up having to buy our own. So, as mentioned before, the 3-in-1 phone charger came with a cooling system. However, the cooling system was not that great, and we wanted to improve upon it. And this is the data from it. So the 3-in-1 phone charger thing came with a ceramic cup, and we learned that a ceramic cup is very useful when conducting temperatures. So we decided to sand down the bottom, and we decided to use it in our other tests. It's the data from it. So after a while and a lot of research, we finally found a Peltier system that actually worked, and it could actually freeze water. And we decided to test what metals worked best with it. We thought of using aluminum. However, the bottom of the cup did not work because it's not flat. And then we found copper after testing a bunch of pennies, and it turned out to be extremely conductive. So this is our test from when we put ice in our system, and it didn't melt that much.
Now we'll move on to the 3D printing section. So these are rings we 3D printed for this design. There was a sort of metal outsert that we wanted to fit these rings around, and we were able to do this using some of our several 3D printers we have at the school. The next thing we 3D printed was for our cooling prototypes. We 3D printed some fans. The ones on the bottom, the print failed because of how complex the file was. Our 3D printers just weren't able to handle it, but we decided to go with this propeller file on the top, and that worked a lot better, but it wasn't the best at cooling. And we need to power our Peltier systems using these power sources. This is the one we currently use. We had to buy it off of Amazon. All the rest of them are some we tried to use. The bottom two just didn't work entirely. They're ancient. Our three goals that we decided were the most important. Our first one is that we wanted the water bottle to be able to boil water and freeze it. And then we also wanted the water bottle to be able to hold 16 ounces of water, because we found that's just about the standard amount. And we also wanted our water bottle to be affordable to the average adult. And based upon those goals, here are some of our achievements. Our water bottle can maintain water temperature better than a standard insulated water bottle. It's a very lightweight design and compact, and it is affordable. These are some of the constraints we had to work around for our water bottle. We originally thought of going with a refrigeration unit, and that's that first one. It uses Freon to cool water, and Freon is toxic to humans, so we decided to avoid using toxic chemicals in general. And the second one was that the water bottle is going to be difficult to clean no matter what, because we're working with electronics, so that's going to be difficult to make sure water just doesn't hit it. And then the last one was that we wanted to keep our manufacturing costs low since we wanted this water bottle to be affordable. Our original plan of action was to begin with a heating system and a cooling system research so we can get a baseline of what's the best for each. The next one was that we would then move on to testing and collect data from our systems. The third one was that we would prototype for each of them, and then the last one was that we would finalize our design. And I think that's it.
I would like to add a few things by using what we have displayed here. So we went through many stages of temperature gauging, as you saw all our data points, and with our temperature readings, we've seen some problems with them, so there might be some inaccuracies with our data. We started out with this, which just, if you measure something, it turns green and beeps, and it measures surface temperature. This one is used for, has a little red dot, and also does a temperature and has this beep. And we realized being electric has some problems with them because when the batteries die, it can lead to problems. And setting this one up is meant for different materials. And when we're testing on all different materials with and without liquid, it leads to inaccuracies. Also, we had just a regular stick thermometer, which we thought was the most reliable, but only worked when we were using liquids, so that was also a downside to it. And talking about our final system, I'd like to mention that it's made out of 3 parts, just as I showed you before. It has the cup, the Peltier plate, the heat sink, and the fan. And we decided to stack 2 fans to make it even stronger with the flow. And when we were testing the cups, we have sort of like an evolution of different cup designs we've used. We have our starting one, which is the ceramic cup. Then we got 2 aluminum cups, and then we got a flat bottom one, then to our copper one. And I didn't show you any soldering pictures, sorry about that, so we used the soldering iron. And that is a majority of what's here. It's also commonly used with Peltier systems to use thermal paste. Thank you.
So do we have any questions for these guys? They were definitely ambitious, and you could see how my Amazon suggested list is very odd right now. The most common reviews on that 3-in-1 system is people putting the coffee to get hot on the wrong side and the phone on the other wrong side. Lots of melted phone pictures. Any questions?
Can you talk a little bit about your survey process where you got the initial feedback from 136 people?
Yeah, of course. So we created a Google form, and our teacher has access to a lot of emails and stuff. So we set out a Google form and sent it to a bunch of people who are in engineering or any other students she knows. And I believe she sent it to the principal, where he sent it out to as many people as he could. And not too many responded, only the 136. But we got most of our data from those random people.
And that let us know that this is an issue that people want to be solved.
Did you ask them any other questions, or just whether they felt about heating cool?
There was one question that we removed from the slideshow. It was if people wanted to be able to cook food in a water bottle. And surprisingly, I think it was about 70% said they did want that. So I thought that's pretty interesting.
Mm-hmm. Any other questions?
You had mentioned affordable. Did you consider a price point, specific price point you were aiming for?
We didn't. We wanted it to be comparable to a standard water bottle, which I think the Yeti water bottles is what we were looking at, because those are like, I think, top of the line in insulated water bottles. And so we wanted it to be around, what was it, like $30 to $50?
Okay. And is the intent, because you had mentioned earlier, one of the design choices, there were cooling systems out there, but they weren't portable. So is your design intended to be portable?
Yes. Currently, it has to plug into this power source, but we didn't dabble into any.
Battery technology is.
Yeah. We're not electrical engineers. We're just high schoolers.
No,
Yeah.
it's all good. Question I always like to ask in these type of situations, now that you have gone through it, and you've obviously given a lot of thought, and what would, if you were given this assignment again, if you were going to go at it for prototype 2 or a beta version, what would you do different to improve?
That's a really good question.
That's for all.
Does anyone?
Do you want to say it?
Mine didn't have anything to do with it.
Okay. Well, personally, I would have started out with maybe going straight into cooling and get that refined instead of dabbling in so much heating stuff, because that took a lot of time out of researching cooling stuff. And we were talking about previously maybe doing something besides a Peltier plate, because the Peltier system is not a perfect system, and there's a lot of systems out there, but cooling is just very difficult to find perfect. And we were thinking of looking into it more and more, and maybe looking into that the water dispenser that has a giant cooler on it, because that system would work a lot better than the Peltier system if we can get it smaller.
It's the portability, I think, is
Yeah.
probably your biggest engineering challenge.
I think we should have started with our bigger problem first, because we started with heating, as Ariana said before, and I believe that we should have spent more time on cooling, because that is a bigger issue. And
Yeah, it sounds like one of the key takeaways that you guys have learned from this project is really at the very beginning honing in on that problem statement. And it sounds like you had 2 problem statements, heating and cooling, and all engineering and all things in life. I mean, time constraints is always going to be your biggest one, so I think you learned a good valuable lesson in that. Really hone in and focus on what you really want to, fix first. And you guys came to that, which is awesome, which was cooling.
Yeah.
So that's awesome. Well done.
Thank you.
So back here, we are also Zooming this, and I have my former professor from Johns Hopkins who also works at the Naval Academy, and he has some questions. After finishing this project, have you gained any insights on purchasing components as opposed to trying to custom build everything?
Oh, that hit hard.
I think that since we were just building this completely from scratch, I'm really glad that we did purchase parts. Like, for example, we bought this entire system to be able to see how a Peltier system works efficiently. And I'm really glad we did, because this let us realize what we want to do in the future. And it also led us to be able to prototype with some 3D prints, take stuff apart, and just see what we can do with it.
One problem with this design is that a lot of it at our school, we don't have the ability to make everything, because if we're using heating, we really only have access to 3D printers and cutting materials, and we don't have enough metal to just cut, but we have plenty of plastic that wouldn't work in a heat system.
Are we good?
Do you guys have any more questions?
Well, I could ask lots of questions, so well done.
We don't want the two of us to ask you questions.
I'm an electrical engineer, so you don't want me going down that route.
This is right in your field.
Yeah.
I guess the only question I would have is, how did you manage the process? I mean, this is a lot of the science and the data answers, but how did you manage the overall process from start to finish as a team, and sort of lay out the work that you had to do?
we did it. That was kind of our main problem. I feel like if we were to do this again, we definitely would have like a schedule of some sort of what we want to do.
We did, and we also worked on a system of starting out with brainstorming, and then we honed on the brainstorming, and after that we prototype. That's literally in my notes, where we just go through all these different prototypes and kind of like weed out the weaklings and then go with the strong ones. I wish our process would have been better with getting the weaklings out sooner, because we kind of stuck with some of the not perfect systems for too long, which took up a lot of time.
This isn't in their presentation at all, but they also did a lot of like hands-on research. I had an old ice maker at home that they ripped apart and looked at how that cooling system worked, and that's when Freon disappeared from the agenda. So they did, this is the condensed version. They've been giving me half-an-hour presentations every quarter. So they had to combine all those and give you one condensed presentation here. So they have engineering notebooks where they have been documenting, and they got all the data, and there's more research, like I said, that you haven't seen. Okay, we good? Okay, so here's our other group. When do you want to take over for? Do we really have 2 microphones? I didn't know we had 2.
That'd be your sister.
All right, so thank you guys for all coming out. So our main problem that we focused on this year was underwater golf ball harvesting. So to get into some introductions. Do we? Okay, awesome. My name's Ryan Hogan. I'm a senior at Carmel here.
I'm Alex Peltier. I'm also a senior here at Carmel.
I'm Danny Ryazanov. I'm also a senior at Carmel.
And I'm Allison Walker, and I'm a senior at Carmel.
All right, sorry. So our design and problem statements for our project. So our problem statement we're trying to solve is that golf courses require scuba divers to retrieve the golf balls in their ponds, and this is inefficient and not time effective. There is no current solution to this problem, and divers need to be assisted underwater in order to perform these tasks. And our design statement for this project is that this product will retrieve golf balls from underwater with the use of experienced swimmers. It will be more efficient and will assist the divers underwater. This will make it easier and more cost-effective to harvest golf balls for golf course ponds.
All right, so we conducted a few interviews at the start of this process after choosing our topic, just to get a feel for what the industry is like. It's something that none of us are really experienced in, so we can't send out a survey like the other groups did to Carmel students because they don't know anything either. So we kind of had to reach out to specific people in the industry. So we conducted 3 different interviews. The first person was Dave Groley, someone that Danny actually works with at Royal Melbourne Country Club. He's a superintendent at the course, so he's in charge of keeping the grounds clean and nice. Some key takeaways that we got from Dave is that golf courses don't actually have a problem with these balls in the water. They could really care less. They just see it as an extra revenue source, especially for country clubs where more wealthy people are playing golf there. They're going to have nicer balls that are going to be in the water. And so basically what they do is they reach out to these diving companies that have divers and equipment that come out, and they actually get a cut from all of the balls that these diving companies harvest. So they just like the extra money, so they call these guys up twice a year, and they jump in their ponds and grab all the balls out from the bottom. So to get a feel for what our robot would be like in these waters, we asked him, and he said the ponds are between 3 and 10 feet deep. And also something really interesting we got from this interview is that he actually outsources to California for a diver. So this isn't like your local golf ball harvesting business. These are national companies and national people that will fly across the country to just jump in a pool to get some golf balls. The second person is Mark Schmidt, and he's the president of Rawhide Golf Ball Company, which is one of the more innovative companies in the industry right now, located in Fort Branch, Indiana. He's actually been doing this since he was in high school. He got his first diving equipment when he was our age, and he's been doing it ever since. Basically, how he got into the industry was he saw a need for equipment, and he built one of the first big rollers, which we'll show you guys in a little bit. And that has made him a lot of money in the industry. So he said that he can get 20,000 to 50,000 golf balls at once in one cleaning of a course. He said that cleaning was recommended at least once a year by the courses. And what he likes doing is both machinery and divers together, and he says that's most efficient basically depending on how good these waters are is what they're going to use. So of course, golf courses don't like when you drive on their greens. So if there's a pond right next to the greens, they might just use divers there. But if it's in the middle of a fairway, they might just use the roller and put it between two tractors and roll it at the bottom. And that way they can get golf balls without having to send people into the water. He said, if you want to go back. No worries. So he said new machinery is needed in the industry, but he was a very smart guy who kind of talked over our head a little bit because we just didn't understand a lot what he was saying. He was talking about different ideas of how you can improve the winch placement on these golf carts and tractors that pull the rollers, and we were a little confused by that. So we talked to him about it for a little bit, but we moved on from that, and he actually talked to us about a different solution in the industry that Daniel will talk about in a little bit. So the third person we talked to was Jeff Wall, who is the vice president of procurement at PG Golf. This is the biggest golf ball harvesting company in the country. They actually harvest at all the PGA courses, and so it was awesome to get to talk to him. So he brought up three current ways that he knows they harvest golf balls. The main two are going to be divers and rollers, and the last one is mesh wiring, which isn't really that big, but he said they rarely use it. So basically, once they harvest balls, they sell them online, and they sort the balls between 1 through 5, the best ball being a 5A ball. That'd be like, if you have any golfers out there, it'd be like a fresh Pro V1 just taken out of the box, hit into the water, and harvested an hour later. So that'd be like the best ball in the business, and they sell those at $44 a dozen to get a feel for how much money they're actually making off these golf courses. So we also learned that divers are independently contracted and they're paid by the ball. So if we can make something that the divers could actually buy to make them more money, that's also a different customer that we could market this towards. And then there was two factors, if you want to go back. So there's two factors for how many balls are collected, which we kind of knew a little bit, was how many holes are with water. So of course, a course that has more water holes are going to have more balls in the water. And water placement, generally water on the right side of courses are going to have more because righties are mainly in golf here. Most people hit right-handed and they slice the ball to the right. So if the water's on the right side of a course, it's going to have a lot of balls in it generally.
So some prior solutions. So standard divers. This is the most common solution, and most courses actually prefer standard divers. When you have a bunch of rollers, when you have the mesh wiring that stirs up the bottom of the water, causing the water to look dirty, which for golf courses like Royal Melbourne, who don't really care about how the golf balls look or how they are at the bottom, that really hurts them because the water looks dirty to them. Divers also search by a grid pattern, so they basically lay out a giant grid and they'll do section by section, make sure they get the most. What we did learn is that divers actually can't see more than about 6 to 8 inches in front of their face. So they can barely see, so they're mostly doing blind reaching, which could be dangerous for them because they don't know what's under the water. Additionally with that, it does cost more money than any other solution, with being human labor being one of the most expensive things. And then the underwater roller. The underwater roller is going to be the second most widely used one. It's the basic way that they clean ponds out. It's used by, like Ryan mentioned earlier, with 2 tractors and 1 on each side, and they pull this giant roller, which we have a few photo examples of, and they're at a lot bigger of a scale usually, and they'll roll across the bottom, start getting all the golf balls, but they, like I said, they do stir up the bottom a lot. They don't really work well if there's a lot of rocks at the bottom of the ponds. Rollers work well for clean ponds. If they have trees that are lodged, the rollers do get stuck, and some golf courses like Royal Melbourne don't actually allow rollers inside the course. So the next solution that we have that we're going to show you actually costs $30,000. Now, for some courses, $30,000 might solve a lot, but we believe for the $30,000 price of this next item, it really doesn't do enough. So that item is called the grabber. So the grabber is our current solution that's closest to our idea. The grabber, it helps semi-autonomously with collecting golf balls. What it does is you have the standard golf cart, and instead of needing a second golf cart, you actually get the automated robot, which actually is controlled with a joystick by the guy that's in the tractor to act as if it's the second one. So like we said, it is $30,000, and we personally don't justify $30,000 to save one person the job, just because it does do twice the work for the main guy still, and it's going to take about the same time. Also, with the grabber, it's actually, if the pond is not a perfect pond, it does get stuck. And one cool thing we found out about the grabber is if you were to look it up on the internet, you won't find a single thing about it. We have a video that was sent to us by Mark Schmidt, and it's a super undercover project. So it was only sent to the big golf diving companies, and they actually don't publicly promote it anywhere. Can you click the grabber video up top? Yeah, so it's an MP4 file, so we'll play a little bit of it.
It's kind of just remote controlled. There's someone on the other side of the pond that's just driving it over, and it has the winch in the middle of it, and it's just going to start pulling the roller between each of them.
Yeah, so that's a good example for how big it really is. And like it said, it just simply pulls them across. Another thing we were told is if it's not exactly 90 degrees with the other tractor, it actually might pull in the system itself, causing the system to break on its own. So it's a super fidgety system, and we just don't believe that it's worth the price.
Okay, so next I'm going to be talking about the criteria for this project. Okay, so we need our machine to work underwater. Since it is an underwater robot, it has to be able to go in the ponds that would get the balls from it. And then we also want it to be able to pick up a large amount of balls with human interaction at a minimum, just because you don't want to keep putting it in, taking it out, putting it in if it can't pick up a lot of balls. And at the same time, you want human interaction to a minimum, just because you don't want to have a lot of manual labor, because that's going to really just not be better than any of the prior solutions. And then we also wanted the machine to be cost efficient, to be sold to both golf courses or diving companies. Like we said in some of the interviews, the golf companies really don't care that they're in the ponds, but they would like to make money off of it if they could. So we would want to sell to both the golf courses and the diving companies. And we, again, don't think the grabber's worth the $30,000, so that's kind of where our cost efficient wanted to be in. And then next I'm going to talk about some constraints we had for this project. So we have to build it in within this high school, Carmel, and we have a limited budget of around $300. Our designers all only have high school education, and since we're all seniors, that would be 4 years of education at Carmel. We have less than a year time period to build this. We did start in August, but we didn't really get the project started until September with an idea after all the brainstorming. And we don't meet every day at school. Carmel is on a block schedule, so we have 70-minute classes 2 out of 3 of the days. So we don't really have a full year. And then we have limited testing resources. This is mainly because Carmel's not a golf course. We really can't test how many balls are in the pond, and we don't have a pond to test it in at Carmel, so we did have to work around that. So these are some of our prototypes. We started with a land prototype, and this is 1.0, and this didn't pick up golf balls yet. It was more just of a tank drive to see how it would work on different surfaces on the land. We wanted to really get what we were doing down first before we just put it in the water. And so we did a tank drive with the wheels. We thought this would work best on, again, multiple surfaces, because we knew the ponds, it was not going to be just one flat surface. We did add a sensor to it right away, but we didn't end up using it for this prototype, or really any. And then it was just more of a tank for it, so it was all about how it ran on the ground. And then here's a video of it working. You can see that we run it on grass, and then we do run it on the sidewalk as well. So this is just kind of showing that we tested it on multiple surfaces, and it ran pretty good, and it was pretty fast, and we didn't have that many problems with it, but the wheels did fall off with the tank drive. One would come off, we'd have to fully repair it, and it did come off a little often.
All right, so prototype 1.1, which was built off of the first prototype, and there's 2 main parts of this series of the first prototype. that are major differences, and that is the roller and the wheels. So we got rid of the original treads, tank treads, and replaced them with wheels which we found were much more reliable, not the most reliable as some of them fell off here and there and they did not have the greatest traction, but they were a big improvement to the tank drive. And this is also when we decided to start trying to pick up golf balls with it, with our roller, which we 3D printed discs, a series of 7 of them that would pick up golf balls, and we used tape to also help grip the golf balls and bring them into the thing where we have, in which we had a popper inside. And here is a video of the roller in action and our wheels. So as you can see, the design is moving forward and it's picking up some golf balls, but it is having trouble putting them inside of the machine itself. Now the second prototype, which is actually right here, but the first prototype, the second prototype I mean, was only the Powertrain, which was a big deal for us at the time as we had major Powertrain problems with the first one, so we focused a lot of our resources on getting the Powertrain to be much better, and in this one it was much better with almost full reliability. We had no problems with the wheels coming off, and it was much more sturdy, durable, and reliable compared to the first prototypes. And 2.1, which is what you see right here, is when we added the walls, the netting, and the back and the disc, everything. Now, some notable parts of this design is we have an improved roller, and by the way, Ryan will be getting into the popper and the roller evolution shortly. We also changed the wheels around, adding more rubber ones compared to where you could see, you cannot see in here. Could you go back one side, please? These were the original wheels we used, which just did not do well on hard soft surfaces like dirt and mud. And you can go back forward one. But these wheels worked much better, especially in the dirt. They kept traction and they kept it gripped. Another important thing is we also rotated the direction the roller moved. So in theory, it would be moving this way instead of that way with the roller behind. The reason why we did this is the way the discs move with the servo on it, the wheel spins this way, and the other way it was much harder to get the golf balls inside of the machine. But with this way it was able to pick up more and more of them. And we also improved our control hubs and expansion hubs on the side of it, which are much more reliable than they were on the first one, and also allowed for easier controlling of the unit. And here is a video of the second one being in use, and I believe we used a phone to control it. It was much more responsive and was able to pick up more golf balls, as you could see right there. And we also had a net on it, which as you can see right here, the net is still on, which also allowed for it to be removed so you can get the golf balls in and out of it easily. Now, for the testing, our final results. We conducted 3 tests with 10 golf balls, and each of these tests we wanted to see how many golf balls this 2.1 was able to pick up. Our first test it picked up 5 of the 10, the second one 7, and the third one 6, which is 50%, 70%, and 60%. And if we averaged them all together, on average, Prototype 2.1 picked up 6 out of 10 balls and had 60% picking up efficiency.
So Prototype 3.0. Prototype 3.0 is a really new prototype to us. We've only been working on it for about the last 2 weeks. So it is a smaller prototype compared to that one. We use this more of like a proof of concept, but this one does work fully underwater. We'll show you a video in just a little bit and in the photo. So with this prototype, it uses 3 jets to propel it. So it has the back and forward jets and able to turn left and right, which is controlled by a controller, but potentially in the future we would like to make it autonomous. Additionally, we do have a jet on top, so if it does get stuck behind rocks, logs, or just in a tough surface, we're able to actually lift it up and get it out of that positioning. So with Prototype 3.0, this was a kit that we purchased. So with the kit came all the proper equipment we'd need to waterproof it, and additionally we added the roller system, which is the same as Prototype 2.1, just at a smaller scale to match the robot. So here you could see it driving underwater.
All right, so basically throughout all of our prototypes, there's three main components of them. That's going to be the drivetrain, which on this one is going to be the propellers and the wheels. On this one being the motors and the wheels. And there are two other components that personally I focus on a lot, and I'll be talking about it now. So the first one is the roller, which is these ones right here. From the past solutions, that's where we kind of got our inspiration to make something like this. So at the start, you could see it wasn't very pretty. We kind of just 3D printed a few discs and put some tape on the edge, and we kind of hand measured them too, thinking that would be the best way to capture these golf balls, which we were wrong. And so then we thought of a better way to do this, right? So we 3D printed this middle piece, which we called our guides. So if you guys can see in the middle of each one of these, there's going to be an exact measurement of how big a golf ball is, and that's how wide they're going to be. So this made it a lot easier. We weren't relying on hand measurements and super glue to get the right measurement on these. That worked a little better, but not as good as we would have liked. And so we remeasured and 3D printed a third time, and that's when we got our third design, which we don't have on us, but it was something like this. There's a picture right here. And then we moved on to the next one where we added another disc, and yeah, it worked amazing. It would run over these golf balls and it'd pick them up very nicely, and we didn't have any problems with it. And we went to our last design where we just kind of shrunk it because it had to fit in this little baby robot. So we shrunk it into only 3 discs and had the same size guides in the middle of them. So it would still pick up the golf balls at the same rate. So then we have the evolution of the popper, which is what we named these pieces. We like giving them fun names. If you want to go. So we started off with a 3D print that we made using our software, and we 3D printed it. We cut off the front, and it didn't look very pretty, and it didn't work very well either. What would happen a lot of times is the roller would pick up the ball, and it kind of just get stuck in it. It would just sit right here, and the ball wouldn't go into the main part of the robot, was the problem we were seeing a lot. So by fixing that, we would make the incline a little bit more, and it didn't always work. So we kept going, of course, and the third design was a lot fatter. So this was actually on the top of the robot. Dan, you want to grab that for me? So back when we had our robot moving forward, so this would be the front. It was actually on the top of the robot right here, and it would pop out the golf balls that way. We found this did not work very well because it would actually just kick the balls forward. So it would drive forward with the rollers in front, and it just pushed the balls forward. And looking at other designs of above ground pickers, they actually drive over the balls and then pick them up on the back end. So that's what we took inspiration from to make that adjustment. So then our next adjustment was making it a little smaller and putting it on the back of the robot. And that was, again, too flat. It would get stuck again. As you can see, it would just get stuck right here. And so we made our last and final adjustment to make our 10 out of 10. And I've never seen this not work, actually, the one on this robot. I've never seen this one not pop out a ball in it. Every time that we picked up a ball, it pops right into the robot, and it works beautifully. So I'm very proud that we've come up with that design. And then we made it a little smaller so it'd fit into our baby robot. So thank you guys for listening. Do you have any questions for us?
Again, same question. You started now. What have you learned? What would you do different as a next prototype?
I'd say personally, don't do so much above ground prototyping. We kind of got carried away with it, I'd say, of trying to perfect an above ground prototype, thinking we just drop this thing in water and it'd work, which was not the smartest decision. So when we finally were done with our above ground prototype, we had 2 weeks to build this thing. So if we would have had like 3 months to build that, I think we could have come up with something a lot bigger and that would work. We could have tested a lot more. So that's something I wish we did sooner.
And like Ryan said, we were really perfectionists with that land prototype. We wanted to work so well before we dropped it in, but we just waited too long to actually put it in the water. And it's different in the water. You have to do your motors differently. And we were just kind of like, oh, we'll just resin seal it all. That was not the case. That's not how you just make something go in the water. So again, I would probably have like maybe stopped a couple evolutions of the land prototype sooner, just to really get the water prototype, which is the main purpose of it, more of a solid finish.
So they can get an idea, Allison. Why don't you explain how you had to waterproof those motors?
Okay, so it was actually not the most fun day of our lives. We had to put toilet seal in it. They just gave us a tube of toilet seal and a ring of toilet seal, and we just had to like jam pack it in the motors to kind of just, make it waterproof so it would go under. And they just gave us gloves and the wax, and we're like, have the best time. And you can like see it. It is very earwax-like, and it was not a pleasure.
Yeah, so something that we didn't mention as much for 3.1, 3.1 was actually built fully from scratch. So when we got it, it came in just long PVC pipes, and we had an instruction manual, and we had to go off that. So we made a few iterations just to be able to make it work for us, but that whole robot was actually built by like us cutting, us really doing all the hands-on work for it.
And to add to your question too, I think something I wish we did too was we have a budget, and I think we were a little afraid to spend it, honestly. We spent some money on this kit. We didn't really spend money on anything else, and I think that we could have bought things sooner that could have helped us a lot rather than trying to make everything from scratch or trying to find different materials around our classroom that we could use instead of just going online and buying something with the budget we were given.
I'd say that if there was one thing we could have done differently is a little better time management with the robot. As they mentioned before, we spent a lot of time on the land robot, like from December to about early April. We probably were working on that thing. Probably didn't need to put as much time into it, and we should have probably got right into the water robot, which could have been made bigger and better and more efficient in golf ball picking.
We also didn't show this, but we spent about 2 days filling up a kiddie pool to test it. So we probably could have, used that time a little bit better. We did recruit a lot of people. So if you were at Carmel those 2 weeks, you might have seen just a bunch of boys just going back and forth, filling up like 5-gallon buckets of water for our kiddie pool. That's in the engineering room right now.
You had mentioned.
You say that, but those of you that are here that know Carmel, we don't have a pool. So
Yes.
where else were they going to test it?
Exactly.
Bought a pool on Amazon, and we filled it up in the.
And the water thing was like, it was across the hall, so we were making trips. We probably had to do like 100 trips of that water.
100 gallons-ish of water.
Yeah, probably.
You had mentioned moving from land to water was a big obstacle you wish you would have done. What was your biggest engineering obstacle you had to overcome when you went into water?
I would say the biggest one outside of all the waterproofing of the electronics, because that's difficult, would be, and we still were working on it and it's not fully mastered, would be actually getting the golf balls to come up. Because underwater there's a lot more friction than on land, so usually on land when you run over it, it'll get stuck and it'll naturally come up, as in underwater it would actually get just stuck and it would just roll through just because the water's, yeah.
Now with your land prototype, you have a set size that you've built. Did you have a target amount of balls that you wanted to pick up? You talked about being able to pick up 20 to 30,000 in a golf course. Do you know how many that'll hold, or what your target was?
So these prototypes were more made for us as like a proof of concept. So if you were to combine the both of them, that's what we want to do, and then make it on a bigger scale. Like I said, with like Ryan mentioned too, with our $300 budget, we weren't able to go on the big scale just because the parts are expensive. Most of those parts on that robot are actually just taken from our robotics teams here at Carmel, and we just used what we had.
Yeah, I honestly don't know how many could fit. My guess would be about 20, but our idea was to make like a removable bag that would kind of enclose it, and then you'd pull out the bag and it'd be easy transfers. But it would be a lot to pick up 20,000 balls with this little robot. So the goal would be to make it a lot bigger. have it almost like a little dog following a diver and picking up anything that it missed.
But then it would have a bag that you guys would.
Yeah. Would you would like remove, dump out, and then put back in?
That was on there at one point. There's like a 20-foot by 20-foot net.
Yeah. Yeah.
We ordered the net to have a bigger prototype, and it would also probably, I think we were thinking more of like the grabber size, just so it can hold more balls. But again, we don't have the space to really store that big of a machine and work out in the classroom because there's just nowhere to store that much machinery. So we kind of had to keep it small scheme just for like the constraint of working in a high school.
Were they receptive of this idea of you taking, I don't want to say taking their job, but of you like having this assistance for them from a business perspective? And what was their reaction?
They acted pretty positive towards it. Like a lot of the experts we talked to actually were looking for something like this, not like directly, but they were definitely interested in some way of innovating their industry to help increase efficiency.
So Mark Schmidt actually invited us out to his own lab in Fort Branch, Indiana, so we could work on it with him. He'd been telling us he'd been wanting to do something like this for 20 or maybe more than that years, and he just never had the time to do it. So every guy that we talked to, from PG Golf being the biggest company to Mark Schmidt to even Royal Melbourne, all those guys were actually really liked the idea, and they asked us for updates along the way too.
Yeah, getting experts for these guys was rough. We do have an asynchronous, he's in Alaska right now, golf ball diver who says he has patent pendings for other devices as well. And he's going to be watching this video later to give them some feedback as well. So it is something that they're looking for, but finding these people were very difficult. And that is why also the professor from the Naval Academy came in handy as well. The other group, just general engineering type process questions, but this is a very specialized thing.
So like we mentioned with the grabber specifically, most of the stuff, like they really liked hearing about it because they really don't hear about it at all. The grabber, that one was sent to Mark Schmidt directly, just trying to get him to buy it. When you look it up, it just comes up with no results. So a lot of the stuff is super undercover, so when the big companies hear it, they really are interested in it. And they told us early on as we were starting, get something working and we'll definitely actually look at buying it off of you.
Yeah. Actually, most of those experts said they would be willing to buy something off of us once we get something into manufacturing or when we have a final prototype, which is really like awesome to hear in like September. And then we come to now and we're like, wow, that was actually like a lot of work to get to that phase. Like we're not even close to there yet. So it was awesome to hear. I personally had a ton of fun talking to these people. Like, you could tell they don't really talk to people much about their job. So we like talked to them for like an hour, like straight, just about this. And like, they were really fun people to talk to. And that was one of my favorite parts of the year was learning about that.
Like Ryan mentioned earlier, I actually work with Dave Groley. He's the course superintendent at the golf course I caddy for. Every time he sees me, he checks up with me. It's actually really funny. I was caddying with one of his kids, and he goes, wait, my dad was telling me about you. So I know it's actually going around. So that was actually pretty cool to watch.
So how did you guys manage your projects, or I guess the other team? How did you coordinate what needed to be done in your schedule and your plan?
So at the start of the year, we make a big plan that's like, oh, like this is all going to happen, right? Like, oh, we're going to get it all done at this time. But, I mean, of course, that doesn't happen. You get, little things, especially all of us being seniors, like little things that you never thought would come up to. And so we kind of took it step by step. We always had that next step in mind, but not like 3 steps ahead of us. So we were like, all right, so right now we're going to fix the roller. And then next week we're going to fix this. And then after that we're like, I don't know what happens, but then another problem comes up and you fix that problem. Another problem comes up, you fix that problem. And then we move on once we're like, all right, I think we're done with this prototype 1.0. Then we move on to the next one. That's kind of the steps we took along the way. Just kind of having fun building things that worked and then didn't work, so then we fixed it, and then we'd move on when we were satisfied with that prototype.
I would also say, like, things like I feel like the year just crept up on us and it's over before we even knew it, because like for the new drivetrain, we waited a week for it and we were like, oh, a week, you know, we'll fix things here and there. We didn't do that much, but just because we were like, we're waiting on this drivetrain, you know, we got to get it. We were just waiting on it. We're like, we have so much time. And then, you know, again, April came and we're like, oh, we got to waterproof this now, you know. The underwater robots got to go underwater now. So it would just kind of, I feel like, you know, again, being seniors, the year just came by fast, and we had a plan, and we just really wanted to perfect the land prototype, and the plan didn't, as it never does, go perfectly.
That's one of the reasons I love this class, is because I don't assign homework. I don't tell them what to do other than get off their phones and stay on task. My job is just to get them what they need, no matter how ridiculous that request is. So yeah, they're self-paced. At the beginning of the year, I have them make what's called a Gantt chart, where they have all the months and they, you know, decide when they're going to get complete tasks completed. But other than the quarter check-ins, that's it. You know, they decide what they're going to do, when they're going to do it, and they just know that this deadline is here to present to all of you.
The sub plans are pretty easy for this class, because every time we have a sub, it's just work on your project. So it's like
Well, no, part of the sub plans have to be they are allowed to go into the other room. Yes, I know there's a pool in there.
yeah. So I mean, having the same task from October to now is interesting, but there's definitely a lot of little steps along the way that we had to take.